Hello everyone, I'm Neel. I am a final year PhD student at the University of Portsmouth, and I will be speaking about combined proofs and theoretical priors in the context of the effective field theory of dark energy. We are currently in a very interesting time for dark energy research because we have some observational hints that indicate that the behavior of dark energy might be more complex than that of a cosmological constant, which would otherwise be the simplest explanation for dark energy. So we naturally want to know, if not a cosmological constant, then what could be the fundamental physics of dark energy? To answer this, I work in the framework of the effective field theory of dark energy. This is a well-motivated class of models that describes dark energy with a single scalar field. It makes some minimal assumptions about the symmetries of the theory and its mathematical properties about time derivatives. And then it allows for all couplings between the scalar field and gravity that are compatible with these assumptions. So given all these assumptions, this class of models is also equivalent to Hondesky gravity. Now, to get to the EFT of dark energy, we can start with GR and add some things to it. We can start with adding a simple canonical scalar field, and that gives us a new degree of freedom, which is W, the equation of state of dark energy. And here it can be any function of the redshift. We can then modify the kinetic term of the scalar field, and that gives us another new function called alpha k. We can add a coupling between the kinetic terms of the scalar field and the metric, and that gives us one more new function of redshift called alpha b. Then we can add a running or a time dependence to the Planck mass. That gives us another function called alpha m. And finally, we can make the speed of gravitational waves different from the speed of light, and that gives us our last new function in the theory called alpha t. Now here, I'll be focusing on 3 out of these 5 functions. And that is because these 3 are the ones that are the most relevant for predictions of the cosmological background expansion and perturbations. Now, on the previous slide, all these functions were arbitrary functions of redshift. But in practice, we have a finite amount of data and we cannot constrain arbitrary functions. So people typically assume some simple parameterization for their redshift dependence with just a few free parameters, and then they constrain those parameters. In our case, the background expansion is described by the equation of state W, and for it, we assume the well-known W0, WA, or CPL parameterization. And the dark energy perturbations are described by 2 functions of redshift, alpha b and alpha m. And here we make them proportional to omega dark energy, which is the fraction of total energy density in the universe that's contained in dark energy. So we have one free parameter for each of these functions. Now this parameterization is a bit ad hoc, but it also has a mild physical motivation. The physical motivation is that we are assuming that it's the same scalar field that describes both the background expansion and the perturbations of dark energy. And so the effect of the scalar field on the dark energy perturbations should become important at the same time as dark energy becomes important for the background expansion of the universe. So then the simplest thing we can do is to make the effect on perturbations proportional to the energy density of dark energy in the background, which is what we do here. So now I'll come to cosmological probes of dark energy, starting with probes of the background expansion. So we have 3 probes of the effect of dark energy on the background expansion of the universe. We have the CMB, BAOs, and supernovae. And the nice thing about these 3 probes is that they probe different kinds of things on different redshifts. So they are quite complementary to each other. And to show this, I will use this plot from a paper from the Dark Energy Survey collaboration. And if we look at the constraints on W0 and WA here, we see that one single probe, the supernovae, is not very useful for getting constraints on these parameters. Any combination of two probes gives us much better constraints on W0 and WA. And finally, all the three probes together, supernovae, CMB, and BAO, gives us a significant improvement on the W0, WA constraints compared to using any two probes. Now, our idea is to see if we can achieve something similar for the constraints on the perturbations of dark energy. Maybe the improvements that we see in the perturbations won't be as dramatic as what we see for constraints on the background here, but let's see what we get. For the perturbations of dark energy, we have a variety of probes. We have CMB lensing, redshift space distortions, we have the ISW effect, and we have 3 times 2 point, which refers to combined measurements of cosmic shear, galaxy clustering, and galaxy-galaxy lensing. Now, in some sense, all of these are probes of either the growth of density perturbations in the universe or of gravitational lensing of the light that reaches us from either the CMB or distant galaxies. This is a list of all the likelihoods that we consider in this work. Now, we want to combine various probes, but we cannot just take all the likelihoods here, combine them, and get the strongest constraints ever. There is a caveat we need to keep in mind, which is that all our telescopes observe one and the same universe. And when we have measurements from two surveys that have observed the same region of the universe, these measurements are not independent. So we cannot simply combine the two different likelihoods. And usually it is very non-trivial to model the correlations between two different surveys. So what we end up doing is that we simply don't combine any two likelihoods which we expect to be correlated. But despite this caveat, we still have a lot of likelihood combinations that we can perform. And I show that here. In this diagram, we can combine likelihoods from any different blocks because they are independent. However, we avoid combining two likelihoods from the same block because they are observations of similar things in similar regions of the sky, so we would expect them to have correlations. Now I'll start showing some constraints. To start with, I show some constraints from a minimal setup of likelihoods. This minimal setup includes all our probes of the background expansion, which are the CMB, BAO, and supernovae. And we add one extra likelihood specifically to probe late time perturbations of dark energy, which is CMB lensing. And with this minimal setup, these are the constraints that we get on CB and CM, are two parameters describing dark energy perturbations. Now let's see what happens when we add more probes to this combination. So when we add redshift space distortions, we find an improvement in the uncertainties on CM, but we don't see much of a change in CB. Redshift space distortions are a proof of the growth of density perturbations in the late universe. And in the specific parameterization that we have chosen within the EFT of dark energy, which is where the effects on dark energy perturbations are proportional to omega dark energy. It turns out that the growth of structure is affected more by CM than by CB, which is why we see more of an impact on CM when we add RSD. Now let's look at another probe. Now these are our constraints when we add the Planck ISW likelihood to our minimal setup. And now we see that we see some improvement in the constraints on CB, but we don't see much of a change in CM. The ISW effect probes something different than RSDs. It probes the decay of the two gravitational potentials at late times and on large scales. And again, as a consequence of the specific parameterization we have chosen, this is something that is impacted more by CB than by CM. Now, looking at these two contours, we can tell that the RSD and ISW are very complementary probes because they are giving us constraining power in two very different directions in this parameter space of CB and CM. So we can now go ahead and combine these two probes. And what we see here is that when we add both RSD and ISW to our minimal setup, we get much stronger constraints and we see better constraints on both CB and CM because we have added two complementary probes to our minimal setup. The last probe that we have considered is 3 times 2 point, which is a probe of the gravitational lensing of the light that reaches us from different galaxies and which passes through the large scale structure of the universe before getting to us. So we see that the 3 times 2 point likelihood gives us better constraints on CB and also gives us a smaller improvement on CM. We can now go ahead and add RSD to the mix like we did before. And by now we know what to expect. We can see that when we combine both RSD and 3 times 2 point likelihoods with our minimal setup, we see better constraints in both the parameters in our parameter space. So in the previous plots, I was showing how our constraints change depending on what likelihoods we add. But now I want to focus on something that does not change with our likelihoods. So this particular region of the posterior, the boundary here, this, as you can see, this boundary hardly moves, no matter what likelihoods we are using to get our constraints. This might be a bit surprising. It turns out that this boundary of the posterior does not come from the constraining power of our data. Rather, it comes from the theory itself. So, which is what we call a theoretical prior. So, in our theory, we are varying 4 parameters describing dark energy. We have 2 parameters which describe the perturbations, which are CB and CM. And we have 2 parameters which describe the background expansion, which are W0 and WA. And in the priors that we put by hand on these parameters, all these parameters are independent and all of them have wide priors. However, the physics of the scalar field will introduce prior boundaries and correlations in this 4-dimensional space of our varied parameters. Specifically, the physics that is responsible for this boundary inner contours is the gradient stability condition. So what is the gradient stability condition? In the EFT of dark energy, a scalar field will have its own perturbations, and its density and pressure perturbations are related by a speed of sound. The expression for the speed of sound is here, and it is in terms of the free functions in the EFT of dark energy that I had introduced earlier. So we have alpha b appearing explicitly here, alpha m appears here, and the equation of state W appears within the expression for the Hubble parameter here. And this quantity is the square of a speed of sound, which means that it needs to be positive. A negative value of the sound speed squared implies that we have exponentially growing perturbation, which leads to an instability and a breakdown of perturbation theory, which is something that would be ruled out by observations. So we have a condition that the sign of this expression, C squared, has to be larger than 0. And this is a restriction in our 4-dimensional parameter space of CB, CM, W0, and WA. But when we look at a 2-dimensional posterior, like that of CB and CM, this restriction gets projected onto this two-dimensional space. And here it would be a one-dimensional cutoff or a one-dimensional boundary, which depends on the value of W0 and WA. But what we are doing is we are not fixing W0 or WA. We are also varying these parameters and we are constraining them with data. So when we look at posteriors of CB and CM, we have marginalized over the observed posteriors of W0 and WA. So this gradient stability boundary in this CB-CM plane, instead of being a rigid boundary, it is going to be a probability distribution, and we can visualize it with contours. So here I am showing the 1, 2, and 3 sigma contours of these fuzzy gradient stability boundary in a CB and CM plane. And you can see that this boundary has the same orientation as the boundary that we saw in our contours. And this explains why the contours that we see here do not depend on our constraining power on the perturbations on dark energy at all, but rather they depend on the physics that couples the background and perturbations. And they also do depend on what constraints we have on the background. So this boundary depends on our constraints on the background expansion, but so on our constraints on W0 and WA, but not our constraining power on CB and CM. The next thing we can do is we can ask the reverse question. Do the constraints on the perturbations affect the constraints on the background? So do CB and CM affect the constraints on W0 and WA? The answer is yes. And to see this, what we can do is we can try to constrain the background expansion without using any information about the dark energy perturbations and see if there is any difference. So what I have here is this contour is the constraints that we get on the background expansion, but we have removed any information about the dark energy perturbations here. We have done that by replacing the standard CMB likelihoods with a prior on the parameters that only describe the early universe and which only uses information about the early universe to get these priors. So now we don't have any information about dark energy perturbations here. And then we see that when we include information about dark energy perturbations, the constraints on W0 and WA are shifted. This is again due to the gradient stability condition. This condition introduces correlations in the joint parameter space of our 4 parameters, W0, WA, CB, and CM. Because of those correlations, when we have some constraints on the perturbations, and those perturbations are correlated with the background due to the gradient stability condition, we also get some constraints on the background. And this is how our constraining power on perturbations can also affect the constraints that we see on the background. Now I will conclude. I have shown that we have a variety of proofs of dark energy perturbations. These proofs are complementary, and so by combining them, we get significant improvements in our constraints for all of our parameters. I've also shown that our posteriors for these parameters don't only come from the constraining power of our likelihoods, but they also come from theoretical priors, which are due to physics of the EFT of dark energy. Specifically, the theoretical prior that's relevant for us is the gradient stability condition, which couples the physics of the dark energy background and perturbations. So with this, I end my talk. Thank you.